Welcome back to our study of basic physics. We have been investigating kinematics. Hopefully at this point you realize kinematics is a study of the motion of objects. And really what we've done is just describe their motion. Position, velocity, acceleration, displacement, speed, that type of thing. And now we're ready to take that one step further. What causes the motion in the first place? Well, that's dynamics, namely the causes of motion, which is forces, as you probably wouldn't be too surprised to hear. In fact, all the way back to your kindergarten or first play school experiences, you were interacting with others, tussling and pushing and shoving probably, or maybe you were too good of a kid to do that. So you may have come to realize that a force is a push or pull, which is true, that works, but we as a human species have come to understand force a little more deeply than that through the agency of quantum mechanics, what's happening at a very deep level, which may not be very closely connected with what we see in the macro world. We have a deeper understanding of forces. And they reveal or manifest themselves via the agency of what we call particles. The particle exchange theory in particular describes the nature of the interaction of these forces. Now, please don't try and get a clear mental picture of this. If you do, you will be very confused in the description I give you, because I can't give you a clear picture that I don't have myself. So this is in the quantum realm, but it's been demonstrated to be the reality, a more careful description of reality that describes our world. And there are four fundamental forces of nature. We're going to describe them now in terms of what the force is, the carrier associated with the emergence of that force, the relative strength, and what they hold together. So first we have the strong force, and the carrier is the gluon. Well, that probably seems like a reasonably good description of this force because it holds the nucleus together. You know, you think of the nucleus of protons and neutrons. Well, that nucleus would come apart if it wasn't for the gluons, the strong force, holding it together. The relative strength, which I haven't indicated what that is yet, 10 to the 38. The next one is the electromagnetic force. Now, the carrier associated with this is one you're actually familiar with. Everyone watching this probably will have heard of the carrier associated with that force, and it's the photon. So photons, actually virtual photons, are involved in this force. If you have two charged objects and you see the interaction, there's photons being shared back and forth for that force to reveal itself. So that's, again, a little hard to visualize. Relative strength, 10 to the 36. That's a big number too, like 10 to the 38, right? Well, what does it hold together? The atoms and the molecules. If it wasn't for this force, we would have no atoms, we'd have no molecules, we would have no life, because certainly we need molecules, complex nature, to have life. So it's obviously very important. Then we have the weak force. This is a little bit nebulous, perhaps. What is this weak force? Well, like the strong force, it is a short-range force. These two forces are short-range, which means, actually, that their carrier particles are heavy. That seems a little strange, but the heavier the carrier particle is, the more massive, the shorter the range of force. By the way, the electromagnetic force, the photon, it has no mass, and it's a long-term force. In fact, it has no limit to the extent of the force. So back to the weak force, the carrier, W and Z bosons, which are heavy particles that enable that force to manifest itself with a relative strength of 10 to the 28. Now, if it wasn't for this force, we would have no fusion going on in the sun. It's also responsible for the transmutation of nuclear particles, responsible for radioactivity. So And in the process of radioactivity, we actually have nuclei changing from one thing to another. So moving to the last force, probably one that you're most familiar with, and you're wondering why it hasn't come up yet, gravity. And the carrier for gravity is the graviton. I will just mention in passing that we have not yet discovered the graviton. Nevertheless, scientists are convinced it must exist for the standard particle theory, which is very well established to be as we have described it. So now the question comes, what's the relative strength? Well, before we answer, keep in mind that it holds the universe together, the galaxies, the planets, the stars. What is it that holds that together? Well, gravity. So this graviton must be just tremendously huge, right? As I belabor the point, you probably have no real way to, any experience certainly would not inform you as what that relative strength would be. But some of you are probably sensing that there's a little trick going on here. And I've talked about the relative strength, but haven't described relative to what. Well, it turns out it's relative to gravity. So the relative strength of the graviton is 1, 10 to the 0. So all these other forces are in terms of the fundamental force of gravity. The question why it seems to be so dominant in our experience is one we haven't answered yet, and I will on the next slide. To begin to get a handle on these somewhat mysterious relative strengths, consider the hydrogen atom, a single proton and an electron in orbit. So we have a proton and the electron, and there is an electrostatic attraction. Opposites attract, right? So the electron is pulled toward the proton. And that's the electric force. Well, by the same token, they each have mass, and objects that have mass also manifest gravitational forces. So, there is a gravity force, and I'm showing that with a little small arrow here. Now, I wonder if this is the right size of arrow, if the lengths of the arrow represent the relative strength. Well, remember that the electric force is 10 to the 36 times the force of gravity. So I'm sure you realize I've just answered the question. Not only is this too big to compare to this, if indeed the electric force is a trillion times larger than gravity, you would not even see a pixel of this visual graphic. It would be, well, smaller than you can even imagine, because the difference in those forces is incomprehensibly huge. But nevertheless, that's how I'm going to show it to you at the moment. And then let's consider a helium nucleus. Here we go. 2 protons, 2 neutrons. And the sound of the gluons interacting along with the electromagnetic force. So the strong nuclear and the electromagnetic force happening simultaneously. Realizing, of course, that these protons are like charges, so they repel. So the whole nucleus would blow apart if it wasn't for the super strong force gluing them together. The strong being 100 times the electric force. Remember, 10 to the 38 versus 10 to the 36. So that's all fine to conceptually understand, but this is the really mysterious one. Let's consider that a little more. Does it seem to match your experience that the electric force is a trillion times stronger than gravity? Well, that force, as an example, would be like rubbing a balloon on your head and sticking it on the wall. And you realize that the electric force does have some visual effects on our surrounding environment. It can hold a balloon to the wall, or you're scuffing your feet along the floor and snap a doorknob or the nose of your kitty. Oh, don't do that. In any case, maybe it's hard to get a good handle on what the size of that force is, but certainly it doesn't seem like it's stronger than gravity, which you seem to feel right now as you're being pressed into your chair. The effects of gravity are all around you. Well, here is the answer to the question. Ordinary matter has equal numbers of protons and electrons. Now that was a big hint. If ordinary matter is not ionized, it's not charged, then the protons and electrons are equal. The amount of charge in a proton and electron is equal and opposite as well. So atoms are generally neutral. In other words, they don't reveal a charge, because as you look at this hydrogen atom, or any atom for that matter, a long ways away in the macro realm, it's really far away in terms of the scale of that atom. So it looks neutral. It's not revealing the kind of forces that are existing inside, holding the electron to the proton, for instance. Now gravity, it's very weak, extraordinarily weak in comparison to these others, but it's always attractive. So all the material in the universe is collectively trying to attract itself. It's actually matter and energy. But in any case, there's a whole lot of it in the universe, and it just is all positive, so it's all attractive. It just builds and builds and builds. So the gravitational force eventually overwhelms the electromagnetic force in terms of the large scales of the universe. So that's really good, because if the electric force was, well, let's put it this way. If you just have one extra electron or proton compared to the other out of about 10 to the 36, then the electric force would overwhelm the gravitational force, and you wouldn't have the gravitational accumulation of matter to form planets, stars, and therefore people. Well, now the goal of theoretical physics is to unify all these forces that we're talking about into what's known as a grand unified theory, which describes all of these forces combining into one at very early stages, very early epochs in the universe. And basically it's an attempt to understand the universe and all of its forces in one unified theory. And actually, we've made a lot of progress toward that end in particle accelerators over the years. Still quite a ways to go. But there are some basic principles that we've learned that give us a very high degree of confidence that this is probably true, that at very high energies and temperatures of the early universe, that all the four forces were unified into one. So that is a huge goal of physics, to understand the nature of our reality better. And that is a topic that is a little bit beyond us, other than just mention it in passing.